The universe has been expanding for nearly 14 billion years, and for most of that time, we had no way to measure it with any real precision. Now we can measure it with extraordinary precision. Two completely independent methods, using completely different physics, calibrated against completely different stars and signals, disagree with each other at a level that cannot be explained by measurement error. And the more precisely we measure, the wider the gap becomes. That gap is 9%. In everyday terms, 9% sounds like a rounding error. In precision cosmology, where measurements routinely achieve accuracy within 1%, a 9% disagreement between two rigorously independent methods is not a rounding error. It is a signal. It is telling us something about the universe that our best theoretical model does not yet contain. In December 2024, Adam Rees, an astrophysicist at Johns Hopkins University and a co-winner of the 2011 Nobel Prize in Physics, published the results of his most comprehensive analysis to date. 2 years of data from the James Webb Space Telescope, 3 independent measurement techniques, all of them converging on the same number, and that number sits 9% above what the standard model of cosmology predicts. Rees did not frame this cautiously. He said the discrepancy between what we observe and what the model predicts suggests that our understanding of the universe may be incomplete, not slightly off, not in need of minor adjustment. Incomplete. That is an extraordinary statement from a Nobel laureate who helped build the very framework he is now questioning. To understand what that incompleteness might mean, and why it matters so much, you need to understand what exactly is being measured, why 2 different approaches give 2 different answers, and what the universe would have to be doing differently for both of them to be right. The quantity at the center of this dispute is called the Hubble constant. It describes the expansion rate of the universe in a very specific way. For every additional 3.25 million light-years of distance between 2 galaxies, the recession speed between them increases by a fixed amount. That fixed amount, expressed in kilometers per second per megaparsec, is the Hubble constant. The larger the number, the faster the universe is expanding at every scale. Measure it precisely, and you can trace the entire expansion history of the cosmos forward and backward in time. Edwin Hubble first estimated this ratio in 1929, using galaxies close enough to study with the technology of his era. His original value was so high that it implied the universe was younger than Earth itself, which was clearly impossible. That embarrassment kicked off decades of argument about where the true value sat. For most of the 20th century, the field split roughly into 2 camps. One group argued the Hubble constant was closer to 50 kilometers per second per megaparsec. The other insisted it was closer to 100. The bitterness of that argument is difficult to overstate. Careers were made and destroyed over it. Scientific conferences became battlegrounds. The 2 sides barely spoke to each other, and when they did, the conversations were rarely civil. By the early 2000s, precision instruments had finally resolved that old dispute. The Hubble Space Telescope's key project, a major observing program led by Wendy Friedman, published a final answer in 2000. The uncertainty was large enough to be consistent with a range of values, but the central value was clear. The field converged, and the long war seemed to be over. It was not over. As instruments improved and measurement techniques sharpened, a new split appeared, smaller than the old one in raw numbers but far more troubling in its implications. Because this time, both sides had excellent data, rigorous methodology, and independently verified results, and the discrepancy was not going away. It was getting worse. The modern version of the dispute comes down to 2 fundamentally different approaches to the same question. And the approaches are so different in their foundations that it is almost impossible for both of them to be simultaneously wrong in a way that produces the same gap. The first approach reads the universe backward in time. The European Space Agency's Planck satellite spent 4.5 years mapping the cosmic microwave background. the faint bath of radiation that fills the entire universe today as a cold whisper of the enormous heat that existed shortly after the Big Bang. This radiation was released when the universe was approximately 380,000 years old, at a moment when the cosmos had cooled just enough for electrons and protons to combine into neutral hydrogen atoms, allowing light to travel freely for the first time. That event is called recombination, and the light released during it has been traveling through space ever since, its wavelength stretched by the expansion of space from visible and infrared light all the way down to microwave frequencies. The pattern of temperature variations in the cosmic microwave background is extraordinarily detailed. Tiny fluctuations of roughly 1 part in 100,000 from one direction of the sky to another encode the physics of the early universe, with a precision that cosmologists once could only dream of reaching. The locations of peaks and troughs in the angular pattern of these fluctuations are determined by the interplay of gravity pulling matter together, radiation pressure pushing it apart, and the speed at which sound waves could propagate through the primordial plasma before recombination. Planck measured this pattern across the entire sky with angular resolution of roughly 5 arc-minutes, extracting the values of 6 cosmological parameters with precision at the 1% level. Those 6 parameters describe the early universe completely within the framework of the standard cosmological model. The density of ordinary matter, the density of dark matter, the density of dark energy, the amplitude and spectral index of the primordial density fluctuations that seeded structure formation, and the optical depth to the epoch when the first stars began ionizing the neutral hydrogen of the post-recombination universe. From those 6 parameters, everything else in the model can be derived, including what the Hubble constant should be today, given the full expansion history from the recombination epoch to the present moment. Planck's prediction, approximately 67 kilometers per second per megaparsec. The second approach does not model anything. It measures the expansion directly in the present universe, using a chain of overlapping distance measurement techniques that extend outward from nearby stars to galaxies hundreds of millions of light years away. This chain is called the cosmic distance ladder, and it is exactly what the name suggests. A series of rungs, each one calibrated against the last, each one reaching further into the cosmos. The first rung uses Cepheid variable stars. These are giant pulsating stars, typically 10 to 50 times the mass of the Sun and several thousand to 100,000 times more luminous, that expand and contract in a regular rhythm. In 1912, a Harvard astronomer named Henrietta Swan-Leavitt was studying Cepheid variables in the Small Magellanic Cloud, a satellite galaxy of the Milky Way. Because all the stars in the Small Magellanic Cloud are at roughly the same distance from Earth, any differences in their apparent brightness must reflect genuine differences in their true luminosity. When Leavitt plotted the pulsation periods of 25 Cepheids against their apparent magnitudes, she found a tight, clean relationship. Longer period means brighter star, always. That relationship, now called Leavitt's law, is one of the most powerful tools in the history of astronomy. Measure a Cepheid's pulsation period from anywhere in the universe, and you know how luminous it actually is. Compare that true luminosity to how bright the star appears from Earth, and you can calculate the distance with precision. No assumptions about the star's composition, age, or environment, just geometry. The physics underlying this elegant relationship is worth understanding because it illuminates why the measurements are trusted. A Cepheid pulsates because of an instability in its outer layers driven by a mechanism called the Kappa mechanism. At specific temperatures, singly ionized helium becomes more opaque to radiation when compressed, rather than less opaque as most gases do. When the outer layers of the star contract under gravity, this helium layer traps the escaping radiation, building up pressure that drives the layers back outward. As the layers expand, the helium ionizes more completely, becomes transparent again, and the pressure drops, allowing the layers to fall inward again. The cycle repeats with a period that depends on the star's mean density and therefore on its luminosity. The physics is well understood. The relationship is real, stable, and physically motivated. The second rung of the distance ladder uses a specific type of exploding star called a type Ia supernova. These explosions occur when a white dwarf star, the compressed remnant of a dead sun, roughly the size of Earth, but with the mass of our sun, accumulates enough material from a companion star to approach the Chandrasekhar limit. Approximately 1.4 solar masses, the maximum mass that can be supported by the quantum mechanical pressure of electrons. When the white dwarf approaches this limit, electron pressure fails, the star collapses and then detonates in a runaway thermonuclear explosion that destroys it completely. Because the trigger mass is always approximately the same, the amount of material detonating is always approximately the same, and the peak brightness of the explosion is approximately standardized. This makes type Ia supernovae what astronomers call standard candles, objects whose true brightness can be inferred from their observed characteristics, allowing apparent brightness to be converted into distance. The standardization procedure, developed by astronomer Mark Phillips in 1993, showed that the color and decline rate of a supernova's light curve correlate with its peak luminosity in a way that allows precise calibration. Type Ia supernovae reach out across hundreds of millions of light years, far beyond where individual Cepheid stars can be resolved. The Cepheids calibrate the supernovae. The supernovae reach across the cosmos. Combine those distances with the recession speeds of the galaxies containing them, and you get the Hubble constant. Adam Rees's team, operating under the name SH0Es, which stands for supernova H0 for the equation of state, built the most precise version of this measurement ever assembled. Their result: 73 kilometers per second per megaparsec. 73 versus 67, 9%. In precision cosmology, that is a chasm. For several years, the scientific community hoped the discrepancy was a measurement artifact. The most obvious candidate was a phenomenon called stellar crowding, sometimes called blending. Cepheid variables tend to live in the dense, dusty disks of actively star-forming galaxies. When the Hubble Space Telescope imaged these stars, its cameras sometimes blended the light from neighboring stars with the Cepheid's own light, making the variable star appear brighter than it actually was. Brighter Cepheids meant shorter calculated distances. Shorter distances meant a higher derived Hubble constant. The logic was clean and testable. Fix the blending, fix the measurement, close the gap. The James Webb Space Telescope was built to settle this. Webb orbits the Sun approximately 1.5 million kilometers from Earth, well beyond our planet's atmospheric interference and thermal emission. Its primary mirror, 6.5 meters across and coated in gold, collects infrared light with a sensitivity that makes Hubble's capabilities look primitive by comparison. Webb's infrared vision can cut through dust and distinguish individual stars in crowded regions that Hubble blurs into a smear of combined light. If stellar blending was inflating the Cepheid brightness measurements, Webb would catch it. The Cepheids would look dimmer. The distances would lengthen. The Hubble constant would fall back toward 67. Some astronomers were already preparing their analysis of what this resolution would mean for cosmology. The crisis, they assumed, was about to become a footnote. That is not what happened. Webb confirmed Hubble's Cepheid measurements with striking precision. The stars looked the same. The distances held. The expansion rate stayed at 73. In early 2024, the SH0Es team published their findings in the astrophysical journal Letters. They had extended Webb observations across 5 host galaxies, measuring nearly 1,000 Cepheids and calibrating the distances to 8 type Ia supernovae. The sample stretched all the way to a galaxy called NGC 5468, roughly 130 million light-years from Earth. Their conclusion was unambiguous. Systematic measurement error from stellar blending could be ruled out with very high statistical confidence. Ries's response was measured. He said that with the known errors eliminated, what remains is the possibility that we have misunderstood the universe. At a cosmology conference in 2019, Ries had asked David Gross, a Nobel laureate in particle physics, whether the community should start calling the discrepancy a problem. Gross corrected him. "Do not call it a tension," Gross said. "Do not call it a problem, call it a crisis." 5 years later, it still is, and the Webb data has only sharpened the knife. Not everyone is equally convinced. Wendy Friedman, an astronomer at the University of Chicago who led the original Hubble Space Telescope key project that established the modern Hubble constant measurement in 2000, has spent years constructing an independent version of the cosmic distance ladder that relies less heavily on Cepheids. Her concern is that Cepheid variables, despite Leavitt's law, may harbor systematic errors related to their chemical composition, their surrounding dust, or the crowded environments they inhabit. To guard against these biases, her team uses additional types of standard candles. Red giant stars, which reach a consistent peak brightness at a specific evolutionary transition. In a class called JWST stars, carbon-rich stars found in the outer, less crowded regions of galaxies where dust and blending are less likely to cause problems. When Friedman's team published their own Webb analysis in August 2024, their results were internally inconsistent in an unsettling way. Their red giant and JWST measurements came in around 68 to 70, consistent with Planck's prediction. Their Cepheid measurement came in near 72, but with larger uncertainties. Their combined result landed around 70, sitting between the two camps like a referee who cannot fully endorse either side. Saul Perlmutter, another Nobel laureate who reviewed Friedman's data before its release, noted something important. The results suggested there might be tension within the star-based measurements themselves, before you even compare them to the cosmic microwave background. That was a different kind of problem. It implied that the cosmic distance ladder, a tool astronomers have trusted for a century, might carry unresolved systematic uncertainties at its foundation that no single telescope could resolve alone. Ries pushed back, arguing that Friedman's team had used a smaller and potentially unrepresentative sample of type Ia supernovae, which could bias their result downward. The disagreement between these two teams has become one of the most closely watched scientific rivalries of the current era. Two groups of careful, accomplished astronomers looking at the same sky and drawing different conclusions. Both groups led by scientists who have won or reviewed the highest honors in physics. Both groups using instruments that represent the pinnacle of human technological achievement. Both groups finding things that cannot both be true if the standard model is correct. The statistical language of the tension is worth understanding because it reveals exactly how serious this situation has become. When scientists report a measurement or a discrepancy, they express their confidence in terms of sigma, the Greek letter representing the standard deviation of a normal distribution. A 1 sigma discrepancy means there is roughly a 32% chance the result could arise from random fluctuation. 2 sigma means about 5%. 3 sigma is sometimes called evidence in particle physics, corresponding to a roughly 3 in 1,000 chance of a statistical fluke. 5 sigma is the gold standard for a discovery in high-energy physics, corresponding to roughly a 1 in 3.5 million chance that the result is coincidental. The Hubble tension currently sits at approximately 5 sigma. It has been steadily growing from a 2 sigma hint in the early 2010s to 3 sigma, to 4 sigma, and now to 5. Each time a new measurement has come in, instead of the tension relaxing, it has sharpened. The most recent Webb data has not reduced the gap. It has confirmed it. 5 sigma does not mean certainty. It means that if the standard model were correct and there were no new physics, The probability of observing this discrepancy by chance is roughly 1 in 3.5 million. The scientific community has moved beyond asking whether the tension is real and toward asking what is causing it. While the Hubble tension was still being processed, Webb delivered a second shock. Almost from the moment it began observing the deep universe, Webb found galaxies that appeared far too massive to exist at the distances where they were found. The telescope was designed to look back to within a few hundred million years of the Big Bang and watch the first galaxies forming out of the primordial darkness. The expectation was that these early galaxies would be small, irregular, chaotic systems, nothing like the grand spirals and ellipticals we see in our cosmic neighborhood today. The Standard Model's predictions were precise. At redshifts of 7, 8, 10, and higher, corresponding to the universe when it was less than 1 billion years old, galaxies should be dim, compact, and lightweight. What Webb found instead were galaxies that rivaled the Milky Way in mass, fully assembled and luminous at distances where the Standard Model simply did not have enough time to build them. Mike Boylan-Colchin, an astronomer at the University of Texas at Austin, analyzed 6 of the most extreme early galaxy candidates and published the results in Nature Astronomy. His conclusion was stark. To form galaxies that massive in the available time, nearly every atom of gas in their surrounding dark matter halos would need to have converted into stars. Under normal conditions, that conversion efficiency sits around 10%. The remaining 90% of the gas gets too hot, gets blown away by radiation from newly formed stars, or simply never collapses. These early galaxy candidates appeared to be operating at 100% efficiency. No model in existence produces that. Then came a partial correction, and it illustrates how carefully Webb's data needs to be interpreted. Catherine Tyrowski, a graduate student at the University of Texas, led a study published in mid-2024 that re-examined the massive early galaxy candidates. She found that many of them were being fooled by their own black holes. These galaxies, which astronomers nicknamed little red dots because of their compact appearance and characteristic infrared color, harbored black holes that were voraciously consuming surrounding gas. As material falls toward a black hole, it forms a swirling disk of gas and dust that heats to extreme temperatures, radiating enormous amounts of light, sometimes outshining an entire galaxy of hundreds of billions of stars. From billions of light years away, through Webb's cameras, a galaxy with an actively feeding black hole at its center can look almost identical to a galaxy containing 10 times as many stars. The telescope measures brightness. Brightness is usually a reliable proxy for stellar mass. In these cases, it was not. Once the contaminated little red dot galaxies were removed from the sample, the remaining galaxies fit reasonably well within the Standard Model's predictions. Stephen Finkelstein, Tyrowski's advisor, was direct about it. There is no crisis in terms of the standard cosmological model, he said, based on what the galaxies at those distances show. The story did not end there. Even after removing the contaminated sample, roughly twice as many massive early galaxies remained as the Standard Model expects. The excess was not catastrophic, not enough to break the model, but it was consistent and real. Tyrowski herself suggested that stars may have formed faster in the very early universe than they do today. The denser, more tightly packed conditions shortly after the Big Bang may have made it harder for gas to escape during star formation, allowing the process to run more efficiently than modern star-forming regions permit. It is a plausible explanation, but it still requires adjustments to how we model galaxy formation in the first billion years of cosmic history. And then in early 2025, Webb found something else. A massive spiral galaxy, quickly nicknamed the Big Wheel, existed within the first 2 billion years of the universe. Spiral structure is not something that forms quickly. Building a coherent rotating spiral disk requires a relatively quiet gravitational history, sustained accretion of gas without catastrophic mergers, enough time for differential rotation to wind stellar arms into their characteristic pattern. In a young, turbulent universe dominated by rapid merging and chaotic growth, mature spirals should not exist yet. Thembiu Nanyakara, one of the astronomers who discovered the Big Wheel, noted that the galaxy either assembled its mass in an unusually orderly way, or it formed most of its stars in place without the violent collisions that typically build large galaxies in the Standard Model. Meanwhile, a separate Cambridge team used Webb to study over 250 galaxies from that same era and found almost the opposite pattern. Most of the early galaxies they examined were chaotic, turbulent, clumpy systems that had not remotely settled into smooth, rotating disks. The early universe, Webb revealed, contained both messy adolescent galaxies and at least one remarkably mature spiral existing in the same epoch. That is a contradiction the Standard Model does not handle gracefully. Then there are the elongated galaxies. A study published in Nature Astronomy in late 2025, led by Alvaro Pozo and including researchers from MIT, Harvard, and the Academia Sinica Institute of Astronomy and Astrophysics in Taipei, found that many young galaxies observed by Webb appear strikingly elongated, stretched out in one direction like cosmic cigars. These prolate shapes, elongated along a single axis rather than flattened into a disk, do not match the predictions of cold dark matter models, which form the structural backbone of standard cosmology. Cold dark matter is the dominant form of dark matter that the Standard Model proposes. The term cold does not refer to temperature in the conventional sense. It refers to the speed of dark matter particles relative to the speed of light. Cold dark matter particles are assumed to be slow-moving, heavy, and effectively collisionless. This property determines how dark matter clumps together in the early universe and how those clumps seed the formation of galaxies. The elongated galaxy shapes Webb is finding do not match what cold dark matter predicts. They do, however, match predictions from two alternative dark matter models: warm dark matter, in which dark matter particles are lighter and move faster, and wave dark matter, also called fuzzy dark matter, in which dark matter behaves as a quantum wave field with a characteristic wavelength on astronomical scales. In both of these alternatives, the filaments of large-scale cosmic structure are smoother, and gas and stars can flow along them in elongated streams, naturally producing the prolate shapes Webb is observing. The distinction is not a minor cosmetic detail. Cold dark matter is not just one ingredient in the Standard Model. It is the scaffolding. It determines where galaxies form, how they cluster, how the web of cosmic structure looks on the largest scales. If dark matter's fundamental properties differ from what cold dark matter models assume, the ripples from that change propagate through nearly every prediction cosmology makes. Dark matter in general deserves a moment here because it is one of the more extraordinary features of our current understanding. We know dark matter exists. The evidence for its existence is not in question and comes from multiple completely independent lines of observation. Vera Rubin and Kent Ford's galaxy rotation measurements in the 1970s showed that the outer regions of galaxies rotate just as fast as the inner regions, when they should rotate more slowly if gravity falls off with distance the way it does in the solar system. The only explanation that works is unseen mass, a halo of dark matter surrounding and permeating each galaxy, contributing the gravitational glue that holds the spiral structure together. The bending of light around galaxy clusters reveals more mass than the visible galaxies contain. The detailed structure of the cosmic microwave background encodes the signature of dark matter's influence in the early universe. The large-scale structure of the cosmos matches precisely the pattern that cold dark matter simulations produce. What is in question now is not whether dark matter exists, but what it actually is. Cold dark matter models assume particles that are heavy, slow, and effectively point-like. They clump together under gravity in a specific way, forming halos with a characteristic density profile, dense at the center and thinning toward the edges. These halos seed galaxy formation. Gas falls into them, cools and collapses into stars. This framework works extraordinarily well on large scales, but on the scales of individual galaxies and their smaller companions, cold dark matter predictions have faced persistent problems for decades. The models predict far more small dark matter clumps than we observe as small galaxies. This is called the missing satellites problem. The models also predict that the density of dark matter at the very centers of galaxies should be very high, forming what is called a cusp, but observations of many dwarf galaxies suggest the dark matter density flattens out at the center into a core rather than rising to a cusp. And the models predict that the most massive satellite galaxies of the Milky Way should be denser than they are. They are not. Now Webb is adding elongated galaxy shapes to the list of things that warm or wave dark matter explains better than the cold version does. Wave dark matter is perhaps the most exotic of the mainstream alternatives. In this model, dark matter is an extremely light boson, a particle with a mass roughly 22 orders of magnitude smaller than the electron. At such a tiny mass, quantum mechanical effects become relevant at astronomical scales. The characteristic wavelength of the particle, the scale over which quantum wave behavior becomes important, would be roughly 3,000 light-years. On scales smaller than this, dark matter would behave not as a collection of individual particles, but as a coherent quantum wave field, unable to clump tightly because quantum pressure resists compression below the characteristic wavelength. This behavior would naturally resolve the cusp core problem in dwarf galaxies, reduce the predicted number of small satellite galaxies, and create the kind of smooth, coherent filamentary structure along which gas could flow to form the elongated prolate galaxy, shapes that Webb is finding. The challenge is that the characteristic scale may need to be much smaller than a kiloparsec to be consistent with observations of the Lyman alpha forest, the pattern of hydrogen absorption in the spectra of distant quasars. If that is right, fuzzy dark matter cannot solve the small-scale problems and much of its appeal evaporates. This is the state of dark matter physics right now. Multiple models are viable. Multiple observations favor different alternatives. No single candidate perfectly fits everything, and until a dark matter particle is directly detected in a laboratory experiment, the field will remain in a state of productive tension. Alongside the dark matter problem sits the deeper and stranger problem of dark energy. Dark matter is inferred, but its existence is well established. Dark energy is inferred, and its nature is almost completely unknown. When dark energy was first confirmed in 1998 by two independent teams, the HISE Supernova Search Team and the Supernova Cosmology Project, the discovery was that the expansion of the universe is accelerating. Not just expanding, but expanding faster and faster over time, as if something is pushing galaxies apart at an ever-increasing rate. Saul Perlmutter, Brian Schmidt, and Adam Rees shared the 2011 Nobel Prize in Physics for this discovery. Prior to 1998, everyone had assumed the universe's expansion was slowing down. Gravity should decelerate it. All the matter in the universe is pulling on all the other matter. The expansion should be running out of steam. Instead, it was speeding up. Einstein had actually anticipated this possibility decades earlier, and for entirely the wrong reasons. When he first applied his general theory of relativity to the universe as a whole in 1917, the equations kept producing a dynamic universe, one that was either expanding or contracting. At the time, the conventional wisdom held that the universe was eternal and unchanging. Einstein found this so unacceptable that he added an extra term to his equations, the cosmological constant, a form of energy inherent to empty space that would counteract gravity and hold the universe in a stable state. When Hubble discovered in 1929 that the universe was in fact expanding, Einstein reportedly called the cosmological constant the biggest blunder of his life and removed it from the equations. Then, in 1998, it came back. The acceleration of the universe required exactly the kind of repulsive energy the cosmological constant represented. Empty space itself appeared to contain energy that does not dilute as the universe expands, unlike the energy of radiation or matter, which spreads thinner as space stretches. This constant energy density meant that as the universe grew larger, the total amount of dark energy grew with it, eventually overwhelming the decelerating effect of matter and causing the expansion to accelerate. This is the lambda in lambda CDM, the standard cosmological model, a cosmological constant. A fixed energy density of empty space, unchanging and uniform everywhere in the universe. There is a profound theoretical problem with this picture. When particle physicists calculate what the energy density of empty space should be from first principles using quantum field theory, they get an answer that is roughly 10 to the power of 120 times larger than what we observe. That is not a small discrepancy. 120 orders of magnitude is the largest single disagreement between theory and observation in the history of physics. It is called the cosmological constant problem, and it has been unsolved since the 1990s. The resolution that most physicists silently accept is an unsatisfying one. Some unknown mechanism cancels out almost all of the quantum vacuum energy, leaving behind a tiny residual that matches what we observe. Nobody knows what this mechanism is. No theory predicts it. It simply has to be true because we observe the universe to be the way it is. If the Hubble tension is telling us that the expansion history of the universe is different from what lambda CDM predicts, it might also be saying something about this problem. If dark energy is not a constant but a field that evolves over time, its behavior in the early universe would have been different from its behavior today. That difference would change the expansion history in exactly the way that could produce the Hubble tension. Early results from the Dark Energy Spectroscopic Instrument, currently operating in Arizona on the 4-meter Mayall telescope at Kitt Peak, and conducting the largest three-dimensional survey of galaxy positions ever attempted, showed intriguing hints that dark energy might be evolving. The equation of state of dark energy appears to deviate slightly from the value predicted by a pure cosmological constant. The statistical significance is suggestive, but not yet definitive. More data is coming, but if the deviation holds up, it would mean that both the Planck prediction and the lambda CDM framework need revision, not because the underlying physics is wrong, but because the specific model we have been using to describe dark energy is too simple. It would also change our understanding of the universe's fate. A cosmological constant expands the universe forever at an ever-accelerating rate. Eventually, in tens of billions of years, every galaxy beyond our local group will have receded beyond our cosmological horizon, invisible and unreachable, leaving our galaxy effectively alone in observable space. Trillions of years later, the stars will burn out, and the universe will approach a cold, dark, diffuse equilibrium sometimes called the heat death. A dynamical dark energy field, depending on how it evolves, could produce a very different ending. If dark energy grows stronger over time, the expansion could eventually become so fast that it tears apart not just galaxy clusters but individual galaxies, then solar systems, then planets, then atoms themselves in an event called the Big Rip. If dark energy weakens, the expansion could slow, stop, and reverse, leading to a big crunch. We do not yet know which version of dark energy we have. One of the more serious theoretical proposals for explaining the Hubble tension is called early dark energy. The Standard Model's prediction for the Hubble constant assumes that dark energy has always behaved exactly as it does today. Constant, uniform, acting identically everywhere in space and time. But what if in the first few 100,000 years after the Big Bang, before the cosmic microwave background was emitted, dark energy briefly had a burst of additional activity and then went quiet? Mark Kamiankowski, a cosmologist at Johns Hopkins, has described this as the universe receiving an unexpected kick just after it was born. A brief surge of early dark energy would have slightly altered the size of sound waves in the early universe, changing the scale of features that the Planck satellite measured in the cosmic microwave background. That change would ripple forward through the model's predictions, shifting the expected Hubble constant upward, potentially closing the gap with what Reese measures today. The problem is that early dark energy, while it helps with the Hubble tension, tends to make a second, quieter tension worse. That second tension is called the S8 tension. The S8 parameter describes how clumpy the universe is, how much matter has clustered together into dense concentrations of galaxies and galaxy clusters versus remaining spread smoothly through space. The standard model predicts a specific level of clumpiness based on the initial conditions measured in the cosmic microwave background. When astronomers measure that clumpiness directly, using techniques like weak gravitational lensing, they consistently find slightly less clustering than the model expects. The discrepancy sits at roughly 2 to 3 sigma, less dramatic than the Hubble tension but persistent and pointing in the same direction. Adam Reese has called the S8 tension the little sibling of the Hubble tension, less dramatic, less statistically decisive, but persistent and pointing the same way. If both tensions are real, they may be symptoms of the same underlying problem. Two cracks in the same wall. A solution that fixes the Hubble tension by introducing early dark energy tends to increase the predicted clustering of matter, making the S8 tension worse. The ideal solution needs to simultaneously raise the expansion rate and lower the matter clustering, two effects that do not naturally come together in simple extensions of the standard model. No current proposal has convincingly achieved this decoupling. The existence of large-scale cosmic structures that seem too extreme also adds to the picture. The Boötes void, discovered in 1981, is a nearly spherical empty region roughly 330 million light-years across, containing only about 60 galaxies, where standard models would predict several thousand. The Sloan Great Wall, discovered in 2003, is a filamentary structure roughly 1.37 billion light-years long, larger than cold dark matter simulations typically produce. These anomalies do not decisively falsify the standard model individually, but they add to a growing catalog of observations that, while each ambiguous on its own, collectively point in a consistent direction. The neutrinos add another layer of complexity. These fundamental particles, produced in enormous quantities in the Big Bang and in stellar cores, interact with other matter only through the weak nuclear force and gravity. Every second, roughly 65 billion solar neutrinos pass through every square centimeter of your body without interacting with a single atom. Neutrinos have mass. The discovery that neutrino flavors oscillate into each other, proven definitively in the late 1990s, requires them to have non-zero mass. But the absolute masses of the three neutrino types are not known from particle physics experiments. In cosmology, neutrino mass matters because neutrinos are everywhere and they move fast. Heavier neutrinos slow down the growth of large-scale structure by free streaming out of gravitational wells before they can deepen, which would lower S8. Some analyses have found hints that adjusting neutrino mass might partially address the S8 tension, but the effect is too small to fully resolve either the S8 or Hubble tensions. There is a completely different class of explanations that asks whether the problem lies not in the physics of the early universe, but in our location within the present one. Astronomers have known for decades that we live in a region of the universe that is somewhat underdense, a large void roughly 300 million light-years across, sometimes called the KBC void after the astronomers Keenan, Barger, and Cowie who quantified it in 2013. If we are inside an underdense bubble, galaxies on its edge are falling inward toward the denser surrounding universe, which means we would observe them to be receding slightly faster than the true cosmic expansion rate. This could potentially explain a few percent of the Hubble tension. The problem is that the KBC void, while real, is not deep or large enough to account for the full 9%. Studies find it would produce at most a 1 to 2% upward bias in the locally measured Hubble constant. Some theorists have proposed that we might be inside an even larger underdensity than surveys have mapped, stretching out to perhaps 1 billion light years. Future surveys, particularly Euclid and the Rubin Observatory, will map the galaxy distribution out to much larger distances and either confirm or rule out this possibility. Another class of explanations involves modifications to gravity itself. General relativity has been tested with extraordinary precision in the solar system, in binary pulsars, and in the strong field regime of black hole and neutron star mergers through gravitational waves. It passes every test, but these tests probe gravity at relatively small scales and relatively large densities. On cosmological scales, millions and billions of light years, general relativity has never been tested independently of the assumptions built into the standard cosmological model. If gravity deviates from general relativity on large scales, perhaps by becoming slightly stronger at large distances, or by the gravitational constant varying slowly over cosmic time, the expansion history would differ, and both the Hubble constant and the growth of structure could be altered. No modified gravity theory has yet passed all the observational tests simultaneously while also resolving the Hubble tension. But the field is active, and the constraints are tightening with every new survey. Gravitational waves offer another completely independent handle on the Hubble constant. When two neutron stars spiral together and merge, they release enormous amounts of energy as gravitational waves. The amplitude of those waves depends on the masses of the merging objects and their distance. This means gravitational wave events are themselves a kind of standard siren, requiring no calibration against stellar physics or dust extinction. In 2017, the LIGO and Virgo detectors observed the merger of two neutron stars, an event designated GW 170817. The event was also detected across the electromagnetic spectrum, and the host galaxy NGC 4993 in the constellation Hydra was identified. The Hubble constant derived from this single event was approximately 70 plus or minus 12. With such large uncertainties, one event could not resolve the tension, but the number sat tantalizingly between 67 and 73. As more neutron star mergers are detected and localized to their host galaxies, the gravitational wave estimate will become more precise. Current projections suggest that with roughly 50 well-localized events, the statistical uncertainty could shrink to a few percent, enough to definitively favor one side of the tension or the other. A third independent method uses time delays from gravitational lensing of distant quasars. When a massive galaxy lies almost exactly between Earth and a distant quasar, the galaxy's gravity bends the quasar's light along multiple paths, producing multiple images. Because the light paths have slightly different lengths and pass through regions of slightly different gravitational potential, the light traveling each path arrives at a slightly different time. Changes in the quasar's brightness appear in one image before they appear in the others. Measuring those time delays gives information about the geometry and expansion rate of the universe. A team using this technique on a sample of strong gravitational lenses derived a Hubble constant in the range of 73, consistent with Ries's distance ladder. Other analyses of the same lensing data, using different assumptions about the mass distribution of the lensing galaxies, found values closer to 67. The sensitivity of the method to modeling assumptions is itself informative. It reveals how precisely the mass distribution of lensing galaxies needs to be known before this technique can contribute decisively to the debate. The Gaia Space Telescope represents another critical upcoming test. Gaia, launched in 2013, is the world's most precise parallax machine. It has measured the positions and motions of nearly 2 billion stars with microarcsecond precision, a level of angular resolution roughly equivalent to spotting a coin on the moon from Earth. Its full Cepheid parallax catalog will provide the most rigorous calibration of the distance ladder's bottom rung ever attempted. Parallax is the most direct method of measuring stellar distance, requiring no astrophysical assumptions, just pure geometry. If Gaia's Cepheid parallaxes agree with what is currently used in the distance ladder, the Hubble constant of 73 is confirmed at the most fundamental possible level. If they disagree, the distance ladder needs recalibration, and the tension may partially or fully dissolve. The outcome of the Gaia Cepheid analysis is one of the most anticipated results in cosmology. Not because anyone expects a dramatic surprise, but because it will remove the last major systematic argument available to those who still believe the tension can be explained by measurement error. The Standard Model's extraordinary track record is worth dwelling on because, in the current climate of apparent crisis, it is easy to lose perspective. Lambda CDM is not in collapse. It is not dying. It remains the most precisely successful theory of the large-scale universe ever constructed. The primordial nucleosynthesis predictions of the Standard Model match observations to remarkable precision. About 75% of ordinary matter came out of the Big Bang as hydrogen and 25% as helium. The Standard Model predicts this ratio from the competition between the expansion rate and the nuclear reaction rates governing proton and neutron conversion in the first 3 minutes after the Big Bang. It also predicts the abundance of deuterium, a sensitive probe because deuterium is easily destroyed by further nuclear reactions, so its present abundance reflects very precisely the conditions in the first few minutes. The model's prediction matches the observed deuterium abundance to within a percent. The baryon acoustic oscillation signal, the characteristic scale of galaxy clustering imprinted by sound waves in the primordial plasma, has been measured in multiple galaxy surveys and matches the Standard Model prediction with high precision. The large-scale structure of the universe, the cosmic web of filaments, walls, sheets, and voids that you see when you map the positions of millions of galaxies, is beautifully reproduced by simulations that start from the density fluctuations measured in the CMB and evolve them forward under gravity with cold, dark matter. These simulations, run on the world's largest supercomputers, produce virtual universes that look statistically indistinguishable from the real one when compared on scales larger than a few tens of millions of light years. No competing theory can match this track record. None. The Standard Model is a genuine scientific achievement, one of the great intellectual constructions in human history. But the model is developing fractures that were not visible a decade ago. Fractures that are getting wider, not narrower, as instruments improve. The history of physics offers a useful perspective here. The physics of the late 19th century appeared complete and victorious right up until it was not. The ultraviolet catastrophe and blackbody radiation, the negative result of the Michelson-Morley experiment, the anomalous precession of Mercury's orbit, each was a small, stubborn discrepancy that refused to go away. Each turned out to be a door. The quantum revolution, special relativity, and general relativity did not emerge from confirmation. They emerged from contradiction. Cosmology has its own version of this pattern. In the 1990s, the field faced a different crisis. Measurements of stellar ages suggested that the oldest stars were older than the universe itself. That was obviously impossible. Stars cannot be older than the cosmos that produced the nuclear fuel they burn. The resolution, the discovery in 1998 that the universe's expansion is accelerating, did not just fix the age problem. It revealed that 68% of the entire energy content of the universe had gone completely undetected and unaccounted for in all prior cosmological thinking. What looked like a fatal inconsistency turned out to be the shadow of something enormous. The field did not shrink from that discovery. It expanded along with our conception of what the universe is. What is happening now may be structurally similar. The Hubble tension may be telling us that dark energy does not behave as a fixed cosmological constant, but evolves over time. The early galaxy problem may be telling us that the rules governing how gas collapses into stars in the early universe were different from what our models assume. The elongated galaxy shapes may be telling us that dark matter is lighter or fuzzier or more wave-like than the cold dark matter paradigm predicts. The S8 tension may be telling us that gravity on cosmic scales needs revision, or all of these tensions may share a single source that nobody has identified yet. A missing piece so fundamental that once it is found, the entire picture will rearrange itself into a new coherence. The precision at which these discussions are happening is itself historically remarkable. A discrepancy of 9% in the Hubble constant corresponds to a difference of roughly 6 kilometers per second per megaparsec. In absolute units, that is a difference of about 2 kilometers per second for a galaxy sitting at 1 megaparsec, about 3.25 million light-years from Earth. We are arguing about a recession speed measurement that differs by 2 kilometers per second at a distance of 3.25 million light-years. The universe is approximately 93 billion light-years in diameter, and we are debating its expansion rate to within 2 kilometers per second at a reference distance of 3.25 million light-years. That fact alone is worth pausing over. The scale of what we are measuring, and the precision with which we are measuring it, represents centuries of accumulated scientific effort. From Newton's law of gravitation, to Einstein's general relativity, to Leavitt's period luminosity relation, to the construction of space telescopes that can measure individual stars and galaxies tens of millions of light-years away. All of that history, all of that technology, all of that mathematics has delivered us to a point where we can say, with 5 sigma confidence, that the universe is expanding 9% faster than our best theoretical model predicts, and we genuinely do not know why. New instruments will help resolve this. The European Space Agency's Euclid mission is already in operation, mapping the geometry of the universe on scales no previous telescope has attempted, measuring the pattern of galaxy clustering and gravitational lensing across 10 billion years of cosmic history to produce a three-dimensional map of how dark matter and dark energy have shaped the large-scale structure of the universe. NASA's Nancy Grace Roman Space Telescope, designed as the successor to Hubble for wide-field infrared surveys, will conduct massive surveys of galaxy distribution across billions of light-years, specifically designed to probe whether dark energy has changed over cosmic time. The Rubin Observatory in Chile will observe billions of galaxies and tens of thousands of Type Ia supernovae over the next decade, providing an independent measurement of the Hubble constant with statistical power that dwarfs everything done so far. The Atacama Cosmology Telescope has already produced the most detailed ground-based map of the cosmic microwave background ever made. Its latest data release slightly revised the Planck prediction for the Hubble constant upward, nudging it closer to 70. Not enough to close the gap, but enough to confirm the tension is real and narrow the range of explanations that can account for it. The Dark Energy Spectroscopic Instrument will also measure the growth rate of cosmic structure through a technique called redshift space distortions. When galaxies fall toward overdense regions under gravity, they have a peculiar velocity component on top of the cosmic expansion that shows up as a distortion in how their clustering appears in redshift surveys. The amplitude of that distortion is directly related to the growth rate of structure. In general relativity, the growth rate and the expansion rate are linked in a specific way. If gravity is modified, that relationship changes. If the growth rate measured by the dark energy spectroscopic instrument is consistent with general relativity's prediction, given the expansion rate measured by the distance, latter modified gravity theories are disfavored. If there is a discrepancy, modified gravity gains traction. The cosmic microwave background is also not finished giving up its secrets. The CMB contains information not just in the temperature fluctuations, but in the polarization of the light. Temperature fluctuations arise from density variations in the early universe. Polarization patterns encode the effects of gravitational waves, primordial ripples in spacetime produced during inflation, the hypothetical period of exponential expansion that stretched quantum fluctuations to cosmological scales in the first fractions of a second after the Big Bang. Detection of the characteristic polarization pattern called B-modes produced by primordial gravitational waves would be direct evidence for inflation and would constrain the energy scale at which it occurred. The Simons Observatory in Chile and the proposed CMB-S4 experiment, a network of microwave telescopes in Chile and Antarctica, are designed to search for these signatures with sensitivity far beyond what Planck achieved. The early universe itself deserves more attention as a source of clues. In the very earliest moments after the Big Bang, the universe was dominated by radiation. Photons and other relativistic particles filled space at unimaginable density and temperature. The expansion rate in this radiation-dominated era followed a specific mathematical relationship, proportional to the square root of time. As the universe cooled and matter became the dominant component, the expansion shifted to a different relationship, proportional to time to the 2/3 power. Then, a few billion years ago, dark energy began to dominate over the diluting matter density, and the expansion switched to exponential acceleration. Each of these transitions leaves signatures in the distribution of galaxies and in the CMB that cosmologists use to reconstruct the expansion history. A single value of the cosmological constant fits all of these signatures simultaneously. The same number that describes the current rate of acceleration correctly predicts the transition point where dark energy took over from matter roughly 7 billion years ago. That internal consistency is what makes the Standard Model so compelling and why the Hubble tension is so disturbing. The tension does not just mean the expansion rate is wrong. It means the entire expansion history, as seen from its present endpoint, is wrong in a way that requires the rest of the model to be adjusted to compensate. There is something remarkable about this situation when you step back from the technical details. Human beings, on a rocky planet orbiting an ordinary star in the suburbs of a perfectly unremarkable spiral galaxy, have built instruments sensitive enough to detect the expansion of space itself and measure it to within a few percent. We have traced the history of the cosmos from the first fraction of a second after its birth to its present state, nearly 14 billion years later, using light that has traveled for billions of years to reach our detectors. And having achieved that precision, we have found that the universe does not quite match our predictions by 9%, by twice as many galaxies as expected, by shapes that do not fit the models. That 9% is not an embarrassment. It is perhaps the most valuable number in science right now, because it means the map is wrong in a specific way, and specific wrongness has always pointed toward specific discovery. The Standard Model will either be corrected, extended, or replaced. History suggests the first option is most likely. The correction, when it comes, will probably be something that in retrospect looks obvious, something hiding in data we have been looking at without fully understanding. A different behavior for dark energy in the early universe, a slightly different mass for dark matter particles, a modification to how efficiently early galaxies converted gas into stars. Or it will be something no one has thought of yet, something that arrives from a direction nobody was looking. That is the history of physics. The answer usually comes from the direction nobody expected. What we know right now is that two of the most powerful instruments humanity has ever pointed at the sky are telling us with very high confidence that our model of the universe is missing something real. The James Webb Space Telescope and the Hubble Space Telescope, cross-checked against each other, find the same expansion rate. The Planck satellite, cross-checked against theoretical models of extraordinary precision, finds a different one. Those two answers cannot both be right, and both, as far as anyone can tell, are built on excellent science. The universe, in other words, is disagreeing with us, and the gap between what it is and what we thought it was is where the next version of cosmology will be found. Scientists still do not know what is causing the Hubble tension. They do not know whether early dark energy is real or a mathematical convenience. They do not know whether dark matter is cold, warm, or something else entirely. They do not know why the early universe produced galaxies that appear more massive and more structured than the models allow. They do not know what dark energy fundamentally is, even after 25 years of treating it as a cosmological constant in the equations. These are not admissions of failure. They are the live questions at the edge of what we know, the frontier where telescopes are pointing and theorists are working, and the data is still coming in. The last time cosmology had a physics problem of comparable depth, it produced the discovery of dark energy. That discovery transformed our understanding of the universe more profoundly than anything since the Big Bang theory itself. Whatever comes next may be equally transformative. Every great resolution in the history of physics has opened more questions than it closed. The discovery that matter is made of atoms led immediately to the question of what atoms are made of. The answer, electrons and nuclei, led to the question of what nuclei are made of. The answer, protons and neutrons, led to quarks, and quarks led to quantum chromodynamics, and quantum chromodynamics led to questions about the strong force that are still being worked out today. Each answer is a door into a larger room. Whatever resolves the Hubble tension will open a room we have not seen yet. The data that will resolve this question is not hypothetical. It exists right now, encoded in the photons striking Webb's detectors in the cold dark beyond Earth's orbit. It is in the electromagnetic signatures of gravitational wave events reaching LIGO's mirrors across 4 kilometers of laser-maintained vacuum. It is in the spectral signatures of billions of galaxies being cataloged by the Dark Energy Spectroscopic Instrument. It is in the positions of nearly 2 billion stars being tracked by Gaia to micro-arcsecond precision. It is being gathered, stored, processed, and analyzed by thousands of scientists on every continent. The answer is in there. Someone will find it. If you want to follow this story as it develops, subscribing and staying with this channel means you will be here for the moment when those pieces click into place. These are not abstract questions. They are questions about what the universe actually is, what it is made of, how it began, and what it will become. Every answer changes everything that comes after. The universe has been expanding since the Big Bang. It has been doing so for approximately 13.8 billion years, without any concern for whether our models match. The question that now sits at the center of cosmology is whether it is expanding according to the rules we have written or according to rules we have not yet found. We are close. We can feel the edges of the answer in the data, in the tensions that will not dissolve, in the galaxies that should not exist, in the shapes that should not look the way they do. The precision of our ignorance is itself remarkable. We know exactly what we do not know, and exactly how much data we need to resolve it. The universe has been patient with our measurements for 14 billion years. It will be patient a little longer while we figure out what it has been trying to tell us. The full weight of what the Hubble tension represents only becomes clear when you understand how deeply the standard model has been tested, and how extraordinary it is that anything is capable of challenging it at this level of precision. Consider what the cosmic microwave background actually is. In the first 380,000 years after the Big Bang, the universe was a plasma. Protons and electrons moved freely, and because they were charged, they interacted constantly with photons. Light could not travel more than a short distance before being absorbed and re-emitted. The universe was opaque. It was, in a very real sense, fog all the way down. There was no such thing as a view of anything distant, because light could not reach you from a distance without being scattered on the way. Then, as the universe cooled with expansion, a critical temperature was reached where electrons and protons could combine into neutral hydrogen atoms without being immediately torn apart by the heat of surrounding radiation. This is the recombination epoch. When neutral hydrogen formed, the universe became transparent almost instantly on cosmological timescales. The photons that had been bouncing around in the plasma were suddenly free to travel. And they have been traveling ever since, for nearly 14 billion years, in every direction, filling the entire universe with a bath of radiation that has stretched with the expansion of space from optical wavelengths all the way down to microwaves. That bath of radiation is what Planck measured with such precision. What makes it so extraordinary as a scientific instrument is that it is a snapshot of the universe at the moment it became transparent, imprinted with the pattern of all the density variations that existed at that moment. Those density variations were themselves the echoes of quantum fluctuations that occurred during inflation, blown up to cosmological scales. So the cosmic microwave background is, in a very real sense, a photograph of quantum mechanics at work in the first fraction of a second of cosmic history, magnified by the expansion of the universe, and then preserved for nearly 14 billion years, waiting for us to build instruments sensitive enough to read it. And read it we have. The 6 parameters extracted from the cosmic microwave background by Planck describe the early universe so completely that from them you can calculate, within the framework of the Standard Model, what the universe should look like today. The density and distribution of galaxies, the mass function of galaxy clusters, the abundance of light elements, the large-scale structure of the cosmic web, the baryon acoustic oscillation signal in the galaxy distribution, the age of the universe. All of it flows from those 6 numbers. The agreement between those predictions and direct observations is one of the most impressive intellectual achievements in the history of human science. And yet, from those same 6 numbers, you derive a Hubble constant of 67. And when you measure the Hubble constant directly, with 2 independent space telescopes observing the same stars using the same physics in the same universe, you get 73. Something is wrong somewhere, and neither side can find it. The idea that the problem lies in the very early universe, before recombination, before the cosmic microwave background was emitted, is scientifically appealing because it would explain why the tension has persisted through every measurement improvement. If something happened in the first few 100,000 years of cosmic history that the Standard Model does not account for, then the Standard Model's prediction of 67 would be systematically wrong. Not because of bad physics, but because of missing physics. Physics that operated at an epoch before our best observational window opens. The sound horizon is the key. Before recombination, the universe was a plasma filled with pressure waves, acoustic oscillations driven by the competition between gravity pulling matter together and radiation pressure pushing it apart. These pressure waves traveled at roughly 57% of the speed of light through the primordial plasma. When recombination happened and the plasma froze into neutral hydrogen, the pressure waves stopped. The maximum distance those waves could have traveled before they stopped is called the sound horizon, approximately 440 megaparsecs in the Standard Model. That distance was imprinted as a preferred clustering scale in both the cosmic microwave background and the galaxy distribution. It is the baryon acoustic oscillation ruler. The Planck satellite measures the angular size of the sound horizon in the CMB. To convert angular size into physical size requires knowing the distance to the CMB, which depends on the expansion history, which depends on the Hubble constant. There is a degeneracy between the sound horizon size and the Hubble constant in the Planck analysis. If the sound horizon was actually smaller than the standard model assumes, a smaller angle in the CMB would be explained by a shorter distance, which corresponds to a higher Hubble constant. Early dark energy shrinks the sound horizon by adding extra expansion energy in the period just before recombination. With a smaller sound horizon, the Planck-inferred Hubble constant moves upward. This is the mechanism that makes early dark energy an attractive resolution. But the baryon acoustic oscillation scale as measured in the galaxy distribution provides an independent measurement of the sound horizon size. Most baryon acoustic oscillation measurements have been consistent with the standard model sound horizon. Inserting early dark energy to fix the Hubble tension puts it in mild tension with these independent measurements. Not fatal, but not perfectly clean. The theoretical challenge of constructing a modification to the standard model that simultaneously addresses the Hubble tension, the S8 tension, and the anomalous early galaxy shapes without disrupting any of the model's successes is genuinely difficult. It is not the kind of problem that admits a simple solution. It requires either a very clever single modification with multiple simultaneous effects, or the recognition that what looks like multiple separate problems is actually a single phenomenon viewed from different angles. The history of physics suggests that the latter is more often the case. When the photoelectric effect violated classical predictions, when blackbody radiation gave infinite energy at high frequencies, when Mercury's orbit refused to close perfectly, these were not three separate problems requiring three separate solutions. They were three faces of a single revolution in our understanding of nature. The Hubble tension, the S8 tension, the overabundance of massive early galaxies, and the anomalous galaxy shapes may similarly be multiple faces of a single missing ingredient. The candidates that theorists find most promising share a common feature. They all involve physics that was active in the very early universe and then either decayed or became negligible, leaving behind the specific pattern of discrepancies we observe today. Early dark energy fits this description. Certain models of early dark matter modifications fit it. Some proposals involving extra-relativistic species in the early universe, additional light particles that would have contributed to the energy density at recombination, also fit this pattern. What makes testing these proposals so difficult is that we cannot directly observe the universe before recombination. The cosmic microwave background is our earliest direct observational window into cosmic history. Whatever happened in the first 380,000 years is accessible to us only through its imprints on that background radiation and on the subsequent evolution of structure. The imprints are subtle. Distinguishing early dark energy from slightly different initial conditions or from a modified dark matter model requires extraordinary precision in both the observations and the theoretical calculations. This is why the next generation of CMB experiments matters so much. The Simons Observatory and the proposed CMB-S4 experiment will measure the CMB polarization with sensitivity that dwarfs what Planck achieved. The polarization contains information about both tensor perturbations, gravitational waves from inflation, and scalar perturbations, density fluctuations from inflation. Different inflationary models predict different ratios of tensor to scalar perturbations. Different early universe modifications predict different patterns in the polarization power spectrum. If early dark energy was active before recombination, it left specific signatures in the CMB polarization that have not yet been measured with enough precision to definitively confirm or exclude the model. The coming decade of CMB polarization measurements may be the most powerful test of the early universe physics that underlies the Hubble tension. Meanwhile, the universe itself continues to expand, indifferent to our arguments about the rate at which it does so. The galaxies are moving apart. The photons from ancient explosions are still crossing the cosmos, some of them headed toward Earth, destined to arrive at a telescope mirror at a specific moment in the future, and contribute one more data point to the measurement campaign that will eventually answer the central question of modern cosmology. There is something philosophically striking about the fact that we are having this argument at all. A century ago, the very existence of other galaxies was still being debated. In 1920, the great debate between Harlow Shapley and Heber Curtis played out in Washington, with Shapley arguing that the spiral nebulae visible through telescopes were part of our own Milky Way, and Curtis arguing that they were independent island universes far beyond it. Shapley was wrong. Curtis was right. But Shapley's error is understandable because the distances involved were so vast that they strained every measurement technique available at the time. Within a decade of that debate, Hubble had measured Cepheid variables in the Andromeda galaxy and demonstrated conclusively that it was far outside the Milky Way, at a distance that made it a full-scale galaxy in its own right. And within a few more years, he had measured the recession velocities of dozens of galaxies and discovered that the universe was expanding. The entire conceptual framework of modern cosmology, the Big Bang, the expansion of the universe, the cosmic microwave background, dark matter, dark energy, was constructed in roughly a century. For nearly all of human history before that, the universe was simply the sky, and the sky was simply there, eternal and unchanging and incomprehensible. The fact that we now know the universe is approximately 13.8 billion years old, that it contains roughly 2 trillion galaxies within our observable horizon, that roughly 95% of its total energy content is in forms we cannot directly detect, that it is expanding at a rate we can measure to within a few percent, and that the measurements from 2 different epochs disagree by 9% in a way that the best theoretical framework cannot explain, represents an accumulation of knowledge so extraordinary that it is difficult to fully appreciate from within it. We are not at the end of cosmological discovery. We are clearly not, but we are far enough into it that we can see, with precision, exactly where our understanding breaks down. That is a remarkable place to be. The universe has a structure that runs from the smallest scales of quantum mechanics all the way up to the largest observable structures, the filaments and voids of the cosmic web spanning hundreds of millions of light years. At every scale, the physics we have worked out explains what we see with impressive fidelity. Quantum electrodynamics, the most precisely tested theory in physics, predicts the magnetic moment of the electron to within 1 part in a trillion, and the experiments confirm it. General relativity predicts the timing of pulsar signals, the deflection of light around the sun, the gravitational waveforms from merging black holes, and the precession of Mercury's orbit. All confirmed. The standard model of particle physics describes the behavior of quarks, leptons, and the forces that act on them with extraordinary success. And yet, when you scale up to the size of the observable universe and try to describe its expansion rate, 2 independent methods that each rely on this well-tested physics arrive at different answers. The discrepancy lives at the intersection of the very large and the very small, where quantum mechanics and gravity meet in the early universe, where the initial conditions of the cosmos were set by processes we cannot yet describe. It is precisely in that intersection that our knowledge is most incomplete. The models that will ultimately resolve the Hubble tension will almost certainly involve physics that straddles this boundary. Early dark energy is a field, a quantum field that was active in the very early universe when quantum fluctuations were being stretched to cosmological scales, and then decayed into something we do not observe today. Modified dark matter models invoke quantum mechanical properties, wave-like behavior at kiloparsec scales, to change the gravitational structure of galaxies. Modified gravity theories invoke corrections to general relativity that become important at cosmological scales. In all of these cases, the resolution requires connecting the quantum scale physics of the early universe to the cosmological scale observations of the present. That connection is exactly where our theoretical framework is least complete. General relativity and quantum mechanics, the two foundational theories of modern physics, are mathematically incompatible with each other. They cannot both be exactly right. The reconciliation of these two theories into a quantum theory of gravity remains the deepest unsolved problem in fundamental physics. Cosmology sits at the intersection of both, and the very early universe, the first fraction of a second after the Big Bang, required both to describe. Our standard cosmological model starts just after that epoch, after the quantum gravity era has ended, and the universe is large enough and cool enough to be described by classical general relativity with quantum field theory corrections. The physics of that earliest epoch is unknown, and whatever happened there set the initial conditions for everything that followed. If the initial conditions were slightly different from what the standard model assumes, those differences could propagate forward through the entire subsequent history of the universe, appearing today as persistent discrepancies in things like the Hubble constant and the clumpiness of matter. The Hubble tension may, in this sense, be an echo of physics from the first fractions of a second after the Big Bang, physics we cannot probe directly with any current instrument, showing up in the expansion history and structure of the universe today. If so, the Hubble tension is not just a problem for cosmology. It is a window into the highest energy physics that has ever existed, an energy scale that no particle accelerator can reach and no laboratory can recreate. The universe itself is the only laboratory in which that physics ever operated, and the cosmic microwave background, the large-scale structure, and the expansion history are the only records it left behind. Reading those records with sufficient precision to decode what they say about the first fractions of a second is one of the deepest scientific projects humanity has ever undertaken. The instruments coming online in the current decade were designed with exactly this ambition. The gravitational wave detectors that have been operating since 2015 represent a genuinely new sense for astronomy, a way of detecting the universe that does not rely on electromagnetic radiation at all. Every previous astronomical observation, every telescope in every wavelength, captures photons, light. The gravitational wave detectors capture something entirely different. Distortions in the fabric of spacetime itself, produced by the most violent events in the universe, traveling at the speed of light and passing through everything without being absorbed or scattered. The sensitivity of LIGO and Virgo is almost incomprehensible. To detect a gravitational wave passing through Earth, they must measure a change in the length of their 4-kilometer arms of approximately 1/10,000th the diameter of a proton. To achieve this, they use laser beams bouncing between mirrors polished to atomic precision, suspended on multi-stage pendulums to isolate them from vibration, in vacuum systems so pure that air molecules would drown out the signal, monitored by systems sensitive enough to detect quantum mechanical fluctuations in the laser light itself. And they routinely detect events occurring billions of light years away. The proposed Einstein telescope, a next-generation gravitational wave detector to be built underground in a triangular configuration 10 kilometers on a side, would detect events that are currently too distant or too quiet for existing detectors. It is estimated to accumulate hundreds of thousands of events per year, allowing the gravitational wave Hubble constant measurement to reach precision comparable to electromagnetic methods. If that measurement converges to 73, it confirms the distance ladder, and the tension with Planck becomes essentially impossible to attribute to measurement error. If it converges to 67, the story takes a completely different turn. The accumulation of data from gravitational wave detectors, combined with data from the next generation of CMB experiments, galaxy surveys, and space telescopes, will constrain the theoretical possibilities to a definitive answer within this decade. The answer will come not from a single observation or a single experiment, but from the convergence of many independent lines of evidence, each attacking the problem from a different angle, each ruling out different hypotheses until only one remains. That is how precision cosmology has always worked. Not by the dramatic single discovery, but by the systematic elimination of alternatives and the gradual convergence of independent measurements. It is slower than a dramatic revelation, but it is more reliable. When the measurements converge, they stay converged. The intellectual stakes of this resolution extend beyond cosmology. The standard model of particle physics, which describes the fundamental constituents of matter and 3 of the 4 fundamental forces, has known gaps. It does not include gravity. It does not account for dark matter. It does not explain dark energy or the cosmological constant. It does not explain why the universe contains more matter than antimatter. It does not explain the masses of the neutrinos, even though we know those masses are non-zero. These gaps are not incidental. They are the central unsolved problems of fundamental physics, the physics that resolves the Hubble tension by virtue of operating at the boundary between the very early universe and the present epoch, at the boundary between quantum mechanics and gravity, is likely to illuminate at least some of these gaps. A dynamical dark energy field is itself a candidate for the dark energy that constitutes 68% of the total energy of the universe. A new relativistic species active in the early universe would be a candidate for the particle physics beyond the standard model that theorists have been seeking for decades. The Hubble tension, in this sense, is not a narrow cosmological puzzle. It is one of the places where the frontiers of cosmology, particle physics, and gravitational physics converge. Solving it is likely to require contributions from all 3. The story of how we got here is also worth telling because it reveals how science actually operates in practice, which is often very different from how it is portrayed. The accumulation of the Hubble tension did not happen through a single dramatic experiment. It happened through the steady improvement of measurement precision over 3 decades, the gradual realization that 2 independently derived numbers were incompatible, and the elimination, one by one, of every plausible explanation that did not involve new physics. That process of elimination is not dramatic. It involves years of analysis, recalibration, cross-checking, peer review, and replication. It involves arguments at conferences and competing papers in journals and teams of scientists working independently on the same data and reaching slightly different conclusions. It involves Nobel laureates publicly disagreeing with each other about fundamental questions and being taken seriously by the field because their arguments are built on rigorous data. Science is sometimes described as self-correcting, and it is, but the correction does not happen instantly. It happens over years and decades through the gradual accumulation of evidence that makes old interpretations untenable and new ones unavoidable. In between, there is a period where the evidence is ambiguous enough that reasonable people with the same data can reach different conclusions. The Hubble tension is exactly in that period right now, and the period will end within this decade. What makes this moment historically significant is not just the scientific content, but the speed at which data is accumulating. The amount of cosmological data produced per year today exceeds everything produced in the entire 20th century. Processing and interpreting it requires algorithms, computing power, and theoretical frameworks that are themselves advancing rapidly. Machine learning techniques are being applied to galaxy surveys, supernova classification, and CMB analysis in ways that extract information that would have been inaccessible to previous generations of researchers. The combination of unprecedented data volume, unprecedented instrument sensitivity, and unprecedented computational power means that the questions being asked today can be answered on timescales of years rather than decades. The scientists who will find the answer to the Hubble tension are working right now. Some of them are analyzing Webb data. Some are processing gravitational wave observations. Some are building theoretical models. Some are writing code that will eventually run on data sets that do not yet exist, from surveys that have not yet been completed. The universe has been expanding for nearly 14 billion years. It has witnessed the formation and death of trillions of stars before our sun was born. It contains structures that dwarf anything human imagination could have conceived before we built the instruments to see them. And it operates on principles that we have spent centuries uncovering, principles that are astonishingly precise and internally consistent, and yet occasionally refuse to fully agree with each other. That refusal is an invitation. The universe is not hiding the answer. It is showing us the same answer from multiple directions. We just have not recognized the pattern yet. When we do, when that single missing ingredient reveals itself and the pieces click into place, the universe that emerges from the augmented description will be the one that actually exists, more complete than the model we have now, more strange, more beautiful, and already preparing the next question that we will need another generation of instruments to answer. The relationship between measurement and understanding in cosmology is unusual compared to other sciences, and it is worth dwelling on why. In most experimental sciences, you can design a controlled experiment. You can change one variable at a time, hold everything else constant, and observe the result. You can repeat the experiment as many times as you need to build statistical confidence. You can run a parallel experiment in a different laboratory to verify the result independently. In cosmology, you have one universe and you cannot change it. You cannot go back and measure what the early universe looked like from a different angle. You cannot run the Big Bang again with different initial conditions and compare the results. You have one sky to observe, one expansion history to trace, one cosmic microwave background to decode. The only experiments available to you are more precise observations of the same universe from the same location. What cosmologists have done, with extraordinary creativity, is turn the universe itself into a laboratory. The universe is full of processes that serve as natural experiments. The abundances of light elements produced in the first 3 minutes are a record of the conditions in those first 3 minutes. The cosmic microwave background is a snapshot of the universe at 380,000 years. The baryon acoustic oscillation signal is a ruler, calibrated in the early universe and preserved in the galaxy distribution, that can be measured at different epochs to trace the expansion history. Supernovae are standard candles, calibrated by physics we can test in nearby galaxies and applied to galaxies billions of light years away. Gravitational wave events are standard sirens, calibrated by pure geometry and requiring no astrophysical assumptions. Each of these is an independent measurement of the same universe, calibrated against different physics, affected by different systematic errors. The fact that they tend to agree across a wide range of observations is the most powerful evidence for the standard model. The fact that one specific quantity, the expansion rate today, appears to disagree between early universe and late universe measurements is the most powerful evidence that something is missing. The distinction between early universe and late universe measurements is conceptually important and often underemphasized in public discussions of the Hubble tension. The Planck measurement is not a direct measurement of the expansion rate today. It is a measurement of the early universe at 380,000 years, which is then evolved forward to the present through the standard model to produce a predicted expansion rate for today. The disagreement could therefore reflect something wrong with the model of the early universe, something wrong with the model of how the universe evolved between then and now, or something wrong with both. The late universe direct measurements, Cepheids, supernovae, gravitational waves, lens time delays, do not rely on any model of the early universe. They measure what the expansion is doing today in the nearby universe, using rungs of distance calibrated against nearby objects. If the late universe measurements are right, the universe is expanding faster today than the model predicts. This means the expansion history is different from what the model says, and that difference must be explained by physics that the model currently lacks. The Gaia telescope's upcoming definitive Cepheid parallax catalog is particularly significant in this context because it tests the very foundation of the late universe distance ladder. Parallax is the most fundamental method of measuring distances in astronomy, requiring only the geometry of Earth's orbit around the Sun and the apparent shift in a star's position as the Earth moves from one side of the orbit to the other. No astrophysical assumptions, no stellar physics, just trigonometry. If Gaia's parallax-based distances to Milky Way Cepheids confirm the current calibration of the period-luminosity relationship, then the distance ladder rests on ground that is as solid as anything in astronomy. The Hubble constant of 73 would be confirmed at its most fundamental level, and the burden of explanation would fall entirely on new physics in the early universe or in the intervening expansion history. There is something almost poetic about the fact that the key calibration test for the entire cosmic distance ladder, a chain of measurements that reaches out hundreds of millions of light years to the edges of the observable universe, comes down to measuring the tiny parallax shift of nearby stars in our own galaxy. The longest measurement in astronomy rests ultimately on the shortest, and the question of whether our understanding of the cosmos is complete will be answered in part by the positions of stars that are, cosmically speaking, just next door. The role of individual scientists in this story is also worth acknowledging because science is sometimes presented as an impersonal process of data accumulation, when in reality it is a profoundly human endeavor shaped by the vision, persistence, and courage of individual researchers. Henrietta Swan Leavitt worked at the Harvard College Observatory in the early 20th century as a human computer, one of a group of women hired to classify stellar spectra and perform calculations. The work was demanding, meticulous, and paid less than factory labor. Despite these conditions, Leavitt identified the period-luminosity relationship in Cepheid variables, a discovery that would become the first rung of the cosmic distance ladder and ultimately contribute to the measurement of the Hubble tension a century later. She died in 1921, before the full significance of her discovery was recognized, and before the expanding universe itself was known. Vera Rubin spent decades advocating for the existence of dark matter against a scientific establishment that was slow to take her results seriously. Her rotation curve measurements, which showed that galaxies spin too fast to be held together by visible matter alone, were initially dismissed or ignored by many prominent astronomers. She continued measuring, continued publishing, continued speaking at conferences where her work was undervalued. The existence of dark matter is now a cornerstone of cosmology. She died in 2016, the year before the LIGO gravitational wave detectors made their first detection. She never received the Nobel Prize that her work arguably deserved. Adam Rees and his collaborators published their discovery of the accelerating universe in 1998, when Rees was 28 years old and a postdoctoral researcher. The result was so unexpected, so contrary to the prevailing assumption that gravity was slowing the expansion, that it required years of independent verification before the community accepted it. Rees shared the Nobel Prize in 2011 for a discovery that had been considered controversial for more than a decade after it was published. These stories illustrate that scientific progress depends not just on instruments and data, but on individuals willing to pursue results that challenge established thinking, to fight for the significance of their findings in the face of skepticism, and to accept that the universe is under no obligation to conform to our expectations. The current generation of cosmologists pursuing the Hubble tension are in exactly this position. They have results that challenge the most successful cosmological model in history, obtained with the most powerful instruments ever built, confirmed by multiple independent methods. The challenge is not in establishing the reality of the discrepancy, but in building the theoretical framework that explains it. That theoretical work is happening now, in papers and preprints and conference presentations, and private communications between theorists trying to find the single modification that fits all the data simultaneously. The competitive and collaborative dynamics of modern cosmology are worth understanding because they shape how quickly and reliably the field converges on true answers. Competition between teams like the SH0's collaboration led by Rees and the independent team led by Friedman is scientifically productive. When two careful, skilled groups of scientists using different methods disagree, the scientific community benefits from both groups working to refine their measurements and understand the source of the discrepancy. The truth emerges from the competition between methods, not from any single group's results. At the same time, the large collaborative structures required by modern astronomical surveys, involving hundreds of scientists from dozens of institutions across multiple countries, require extraordinary coordination and trust. The Dark Energy Survey involved over 400 scientists. Planck involved several hundred. The LIGO scientific collaboration has over 1,000 members. These collaborations produce data that no individual or small group could obtain, and they require governance structures, data sharing agreements, and publication policies that are themselves complex scientific and organizational challenges. The Rubin Observatory, when fully operational, will produce 15 terabytes of data every night. Processing that data, identifying transients like supernovae and gravitational microlensing events, measuring galaxy shapes for weak gravitational lensing analysis, tracking the positions of potentially hazardous asteroids, all simultaneously, requires data pipelines of extraordinary complexity that themselves represent major software engineering achievements. Science at this scale is unlike anything that existed even a generation ago. It is a global enterprise, producing data at rates that challenge even modern computing infrastructure, requiring collaboration across language and cultural barriers, managed through distributed networks of researchers who may never meet in person. The Hubble tension is being investigated not by a handful of brilliant individuals working in isolation, but by a global community of thousands of researchers, all contributing different pieces to a puzzle that none of them can solve alone. That collaborative structure is one of the most distinctive and admirable features of modern science. It means that the answer, when it comes, will be the product of many minds working across many decades, many disciplines, and many institutions. It will not belong to any single discoverer. It will belong to the tradition of scientific inquiry that stretches from Leavitt's tables of Cepheid periods in 1912 to Webb's infrared images of galaxies formed in the first billion years of the universe. The universe does not owe us an explanation. It is not trying to tell us anything. It simply is what it is, governed by physics that does not care whether our models match. But we have built instruments sensitive enough to detect the ways in which our models fail, and we have built communities of scientists skilled enough to interpret those failures and use them to build better models. That combination of sensitivity and skill is what makes this moment in cosmology so historically unusual. We are close enough to the answer that we can see its outline. The tensions are too specific and too persistent to be noise. The pattern of discrepancies across multiple independent observations is too consistent to be coincidence. The answer is in the data. It is in the light that has been traveling toward us for billions of years and is just now striking our detectors. It is in the gravitational wave signals that are being recorded at this moment by detectors that were not imagined a century ago. It is in the spectral signatures of billions of galaxies being cataloged by surveys that would have seemed like science fiction to the astronomer who fought over whether the Hubble constant was 50 or 100. The universe has been expanding for nearly 14 billion years. For most of those 14 billion years, there was no one to measure it. Then, in the last fraction of a cosmic second, a species arose on a small rocky planet and began asking questions about the sky. In an even smaller fraction of that fraction, they built instruments capable of detecting the expansion itself and measuring it to within a few percent. And then they found that the measurement did not quite match the theory. that the universe was 9% more eager to expand than the model predicted, that it had assembled galaxies twice as fast as it should have been able to, that the shapes of those early galaxies did not match what the models had led everyone to expect. That discovery, that the map we have drawn with such care and precision is slightly wrong in a specific, measurable way, is not the end of cosmology. It is the next sentence in the longest story that has ever been told. The story of a universe that has been here for 14 billion years, waiting, patient and indifferent, for something in it to develop the curiosity and capability to ask what it is and how it works. We are that something, and we are still asking. There is one more dimension to the Hubble tension that rarely gets the attention it deserves. What it tells us about the nature of scientific knowledge itself, and what it means for a model to be both spectacularly successful and subtly wrong at the same time. The standard model of cosmology, lambda CDM, is an approximation. All scientific models are approximations. The question is always, an approximation of what, and within what domain? Newton's law of gravitation is an extraordinarily good approximation of general relativity for objects moving slowly compared to the speed of light in weak gravitational fields. It is wrong in the vicinity of very massive, compact objects, and for anything moving at relativistic speeds. But it accurately describes the motion of every planet in the solar system, every comet, every spacecraft we have ever launched, to a precision that far exceeds the requirements of any practical application. Lambda CDM is similarly an approximation. It is an extraordinarily good approximation for the universe on scales larger than a few tens of millions of light years, at epochs later than a fraction of a second after the Big Bang, and for the 6 parameters that describe the early universe. It is wrong, apparently, about the specific value of the expansion rate today, slightly wrong about the clustering of matter, and possibly wrong about the fundamental properties of dark matter. That wrongness does not make the model useless. It makes it a signpost. Every place where a model is wrong in a specific, measurable way is a place where deeper physics is waiting to be found. The ultraviolet catastrophe in blackbody radiation, the specific wrong prediction of classical physics that led directly to quantum mechanics, was wrong in a specific way. It predicted infinite energy at high frequencies. That specific wrongness pointed straight to the quantization of energy, which pointed to photons, which pointed to wave-particle duality, which pointed to the entire framework of quantum mechanics. The wrongness was not random. It was structured, and structured wrongness is a map. The Hubble tension is structured wrongness. It is not a vague sense that the model might be incomplete. It is a specific 9% discrepancy in a specific parameter, measured independently by 2 specific types of observations, confirmed by multiple independent teams, growing in statistical significance over time rather than diminishing. That structure is telling us something. We do not yet know exactly what, but the structure itself rules out random measurement error and points toward systematic physics. Consider also the early galaxy problem from this perspective. The excess of massive early galaxies is not a vague anomaly. It is a specific factor of roughly 2 in the number counts of galaxies above a specific mass threshold at specific redshifts. That specificity is constraining. It says the discrepancy is not everywhere and not at all masses, but concentrated at high masses and high redshifts. A model modification that explains a factor of 2 excess in massive early galaxies, while leaving the lower mass galaxy counts unchanged, must be specifically targeted to the physics of massive galaxy formation at early times. That target narrows the theoretical options considerably. Similarly, the prolate galaxy shapes from Webb are not a vague sense that early galaxies look different than expected. They are a specific morphological pattern, elongated along one axis, concentrated in early universe samples, matching specific alternative dark matter predictions. That pattern constrains the space of possible explanations. The S8 tension is not a vague sense that the universe might be less clumpy than predicted. It is a specific number, a specific parameter, measured by multiple independent weak gravitational lensing surveys, and consistently finding values about 2 to 3% below the standard model prediction. The direction and magnitude of the discrepancy is consistent across instruments and sky regions. The convergence of these specific, structured discrepancies toward a common set of possible explanations is the strongest argument that they are all real. Individual measurement artifacts tend to be random and specific to the instrument or technique that produces them. Systematic physics produces consistent patterns across independent observations. The Hubble tension, the S8 tension, the early galaxy excess, and the prolate galaxy shapes are all consistent with modifications to either the very early universe or the fundamental properties of dark matter. That consistency is a clue. The next decade will determine whether this consistency points to a single physical explanation, or whether different discrepancies require different solutions. The data coming from Euclid, Roman, Rubin, the updated LIGO network, the Gaia-Cepheid catalog, and the next generation of CMB experiments will constrain the theoretical space to a definitive answer. When those constraints converge, when all the independent lines of evidence point to the same modification of the standard model, the field will have its answer. That answer will be tested, verified, and eventually taught in university cosmology courses as the resolution of the Hubble tension crisis. The way dark energy is now taught as the resolution of the 1990s cosmological age crisis. Future students will read about the Hubble tension the way current students read about the ultraviolet catastrophe, as a historical turning point that led to something profound. We are inside that turning point right now. We are the ones who found the discrepancy, confirmed it with the most powerful instruments ever built, eliminated every mundane explanation, and established beyond reasonable doubt that the universe is not quite what our best model says it is. The generation of scientists now in graduate school or in the early years of their careers will be the ones who find the answer. They will use instruments that are either just now coming online or still being designed. They will analyze data that is being collected as you read these words. The universe does not care about any of this. It expands at whatever rate it expands at, governed by physics that does not respond to our confusion or our curiosity. The photons crossing the cosmos have been traveling since before life existed on Earth. The gravitational waves carrying information about distant neutron star mergers pass through the entire Earth without interacting with a single atom. The structure of the cosmic web was determined by quantum fluctuation that happened before protons and neutrons existed. All of this has been going on for nearly 14 billion years. We have been paying attention for roughly a century. In that century, we have gone from not knowing that other galaxies existed to measuring the expansion of the universe to within a few percent. From not knowing whether the universe had a beginning to tracing its history back to the first fractions of a second. From not knowing whether atoms existed to discovering the particles inside the nucleus. From not knowing whether gravity could bend light to detecting gravitational waves from black hole mergers a billion light years away. The 9% discrepancy in the Hubble constant is the next step in that century-long journey. It is where the known meets the unknown, where the map runs out and the territory continues. It is where science is alive, where the arguments matter, where the data is still coming in and the outcome is still uncertain. Science advances fastest when it encounters something it cannot explain. The unexplained thing focuses attention, resources, and creativity in a way that confirming existing knowledge never does. The Hubble tension is exactly that kind of thing. A precisely measured, rigorously confirmed, independently verified discrepancy that the best physicists in the world using the best instruments ever built cannot explain with any known physics. It refuses to go away. It grows more significant with every new measurement. It points towards something real and fundamental about the universe. When the answer comes, and it will come, it will not feel like an ending. It will feel like a beginning. Every great resolution in the history of physics has opened more questions than it closed. The resolution of the Hubble tension will open questions we have not yet thought to ask, about physics we have not yet imagined, at scales we have not yet probed. The universe, after all, has never revealed itself to be simpler than we imagined. It has only ever revealed itself to be larger, stranger, and more deeply structured than anything we expected. The room beyond the door is always bigger than the room you were in. We are standing at the door. We can feel it about to open. The sheer scale of what we are discussing, when described in full, has a way of reorienting how you think about everything else. The observable universe extends approximately 46 billion light-years in every direction from Earth. The actual universe may be far larger. We can only see the region from which light has had time to reach us since the Big Bang. Within that observable sphere, there are approximately 2 trillion galaxies. Each galaxy contains hundreds of billions to several trillion stars. Each star is a nuclear furnace running on the same physics we worked out here, converting hydrogen to helium and releasing energy that has powered planetary systems, including at least one that produced life capable of asking why. The cosmic web that connects and organizes all of these galaxies into filaments, walls, and voids is itself structured by dark matter that we cannot see and dark energy that we cannot measure directly. The whole thing is expanding outward at a rate that we can measure precisely enough to find a 9% discrepancy between two independent methods. That 9%, sitting in the largest thing we can conceive, is where the next chapter of cosmology begins. The baryon acoustic oscillation signal is worth understanding in more detail, because it connects the early universe to the late universe in a way that makes the Hubble tension almost tangible. In the first 380,000 years, the universe was a hot plasma of protons, electrons, and photons, all tightly coupled together. The slight overdensities that would eventually become galaxy clusters created pressure waves that propagated outward through the plasma at the speed of sound, roughly 60% of the speed of light. These sound waves were driven by the competition between gravity pulling matter together and radiation pressure pushing it apart. When recombination happened, the pressure waves stopped, frozen in place by the sudden transition from opaque plasma to transparent gas. The maximum distance those waves had traveled became imprinted as a preferred separation distance between galaxy clusters and galaxies, approximately 490 million light-years in the present universe, after accounting for the factor of expansion since recombination. This preferred separation is the baryon acoustic oscillation signal, and it is measurable in the galaxy distribution today. It serves as a standard ruler, a known physical length against which cosmological distances can be calibrated. The sound horizon, the distance those pressure waves traveled before recombination stopped them, is determined by the expansion history of the early universe and by the speed of sound in the primordial plasma. The speed of sound depends on the ratio of radiation pressure to matter density, which is well understood physics. The expansion history of the early universe is determined by the total energy content, including ordinary matter, dark matter, radiation, and any additional components like early dark energy. If early dark energy was present before recombination, it would have slightly increased the total energy density of the early universe, increasing the expansion rate and reducing the time available for the pressure waves to travel. The sound horizon would have been slightly smaller than in the standard model. A smaller sound horizon appears at a slightly different angle in the CMB as seen from Earth, and Planck calibrates its cosmological parameters to explain the observed angular pattern of CMB features. With a smaller sound horizon, the same angular features are explained by a slightly shorter distance, which corresponds to a higher Hubble constant. This is the mechanism by which early dark energy shifts the Planck-inferred Hubble constant upward. The problem, as noted, is that the baryon acoustic oscillation ruler as measured in galaxy surveys is also sensitive to the sound horizon size, and current galaxy surveys find a sound horizon consistent with the standard model. Early dark energy needs to be calibrated carefully enough to fix the Hubble tension without visibly distorting the baryon acoustic oscillation signal, a constraint that significantly limits the allowed range of early dark energy models. The Dark Energy Spectroscopic Instrument is positioned to be the most powerful test of this constraint. By mapping tens of millions of galaxies across more than 11 billion years of cosmic history, it will measure the baryon acoustic oscillation signal at multiple different epochs with unprecedented statistical precision. If early dark energy shifted the sound horizon, the baryon acoustic oscillation ruler should appear slightly different at different redshifts in a pattern that is calculable. The Dark Energy Spectroscopic Instrument data will either show that pattern or rule it out. Early 2024 results from the instrument showed intriguing hints of evolving dark energy, but not yet definitive evidence. The full dataset, accumulated over the instrument's complete survey, will settle the question. The weak gravitational lensing measurements that constrain the S8 tension deserve attention here as well, because the technique is among the most elegant and powerful in modern observational cosmology. As light from distant galaxies travels toward us through the universe, it passes through the gravitational field of all the matter in between, both the visible matter in galaxies and the dark matter in the halos and filaments of the cosmic web. That gravitational field slightly bends the light paths, causing the apparent shapes of distant galaxies to be slightly distorted, stretched, or sheared in patterns that reflect the distribution of mass along the line of sight. The effect is subtle. Typical galaxy images are distorted by only about 1%. Individual galaxies have intrinsic shapes that are much more irregular than 1%. So the lensing signal cannot be extracted from any single galaxy. But if you measure the shapes of millions of galaxies across the sky, the intrinsic shape variations average out, and the remaining coherent pattern of alignment is the weak lensing signal. Its amplitude and angular dependence encode the total mass distribution in the universe as projected onto the sky, which constrains the S8 parameter. Multiple independent surveys, using different telescopes, different sky regions, different analysis codes, all find that the universe is slightly less clumpy than the standard model predicts. The KIDS survey, the Dark Energy survey, the Hyper-SubPrime survey, the European Space Agency's Euclid early results, all pointing the same direction, slightly less clustering than the CMB predicts. The S8 tension is real and persistent, even if it is not yet as statistically decisive as the Hubble tension. The theoretical challenge of reconciling all these observations is compounded by what physicists call the problem of consistency checking. The standard model is a complete and internally consistent mathematical framework. Every parameter is connected to every other parameter through the model's equations. Changing one thing changes predictions across the board. A modification that helps the Hubble tension might hurt the S8 tension. A modification that helps the S8 tension might break the CMB power spectrum fit. A modification that helps the early galaxy problem might alter the baryon acoustic oscillation signal. Finding a single modification that improves all the discrepancies simultaneously without breaking any of the model's successes is an extraordinarily constrained optimization problem. This is why theoretical cosmologists have proposed dozens of candidate solutions, and none of them has yet been confirmed as the answer. The space of viable solutions is being narrowed by each new observation, but it has not yet been narrowed to a single point. The combination of Euclid, Roman, Rubin, the updated gravitational wave detectors, Gaia's Cepheid parallaxes, and the next generation of CMB experiments will narrow it further. Whether they narrow it to a single answer, or to a small set of closely related answers remains to be seen. What is not in doubt is that the answer exists. The universe is real, its expansion rate is what it is, the physics that governs it operates whether or not we understand it. We have enough data to be confident that the standard model is incomplete in specific ways. We have enough theoretical tools to construct and test modifications. We have enough instruments, existing and planned, to distinguish between the candidate explanations. The answer is within reach. The scientific community approaching this problem is not confused or paralyzed. It is focused, resourced, and operating with an urgency appropriate to a genuine frontier. The careers of a generation of young cosmologists will be defined by the resolution of the Hubble tension. The instruments they will use are either operating now or being built now. The data they will analyze is being collected now. There is a certain kind of beauty in the situation that is easy to overlook in the technical details. 14 billion years ago, the universe was an unimaginably dense, hot plasma not much larger than an atom. Every particle, every force, every structure that exists today was contained in that initial state. In the 380,000 years that followed, the plasma expanded and cooled and formed neutral atoms and released the light we now call the cosmic microwave background. In the billions of years after that, gravity organized the matter into galaxies and clusters and the cosmic web. In one of those galaxies, around one of those stars, on one of those planets, life emerged and eventually produced minds capable of asking what the universe is and how it works. Those minds built telescopes and pointed them at the sky. They measured the distances to stars, then to galaxies, then to the edge of the observable universe. They found that the universe is expanding, and then that the expansion is accelerating, and then that the expansion rate measured two different ways gives two different answers by 9%. That 9% is the frontier. It is where the universe's story is still being written, by scientists who are asking the right questions, with instruments sensitive enough to find the answers, in a tradition of inquiry that stretches back through centuries of human curiosity about the sky. The answer is coming, not as a matter of optimism but as a matter of fact. The instruments exist, the methods are proven, the data is accumulating. Whatever the universe is telling us with its 9% disagreement, we will understand it. We always do eventually, when we build instruments sensitive enough to ask the question clearly and minds willing to follow the answer wherever it leads. The universe has been patient. It will be patient a little longer. The final question worth asking, as we stand at this precise boundary between what we know and what we do not, is what it means for a civilization to be capable of asking questions this large. We have measured the age of the universe to within a few percent. We have measured its composition to within a fraction of a percent. We have traced its expansion history back nearly to the beginning. We have found that the beginning itself, the quantum gravity epoch before the first fraction of a second, is inaccessible to direct observation, but may be leaving echoes in the discrepancies we are now measuring. Human science has reached a point where the known unknowns at the frontier of cosmology are not vague, unmeasured quantities. They are specific, precisely constrained gaps. The Hubble constant is known to within a few percent. The discrepancy between the two measurement methods is known to 5 sigma. The parameters of the standard model are known to 1%. The nature of the discrepancy, its persistence through every systematic check, its growth with every improvement in measurement precision, is documented in hundreds of peer-reviewed papers, verified by independent teams, confirmed by 2 separate space telescopes. We are not confused about what the universe looks like. We are confused about why the measurement of one specific quantity, taken by 2 different methods, does not agree. That is an extraordinarily precise kind of confusion. It is the kind of confusion that sits one step away from a major discovery. If you want to stay with these questions as they develop, if you want to be here when the answer arrives, subscribing and remaining part of this ongoing conversation is how you do it. The resolution of the Hubble tension will be one of the major scientific stories of the coming decade, and the steps toward it will be worth following, every one of them. The universe has been expanding for nearly 14 billion years. For most of that time, there was no one to measure it. Now there is, and the measurement is telling us something we do not yet fully understand. That gap between the measurement and the understanding is where the next chapter of human knowledge begins.